Hello everyone. In this video, I would like to discuss the solutions for control systems questions given in recent GATE 2024 electrical paper. Now let us go into the video. The first question is, by the way, from this subject, total 9 marks came in the GATE exam. Now first question, consider the standard second order system of the form omega n square divided by s square plus 2 zeta omega n s plus omega n square with the poles p and p star having negative real parts, that is shown in the figure. The pole locations are given here. Now what is the question? Now consider two such second order systems defined below. System 1, it is having omega is equal to 3 radian per second and theta, where angle theta is also given in this figure. So by seeing the options, it is asking about what is the value of the settling times. Therefore, for this system, what I can calculate, when theta is given, damping ratio is equal to, so simply I can say damping ratio is equal to cos theta. Therefore, here cos theta will be 1 by 2. Damping ratio is 1 by 2. So, in this system 1, you will get quickly damping ratio is equal to 1 by 2. Next, for system 2, we will get damping ratio is cos 70 degree. Cos 70 degree numerical value is 0.342. Now, what is the settling time formula? Here it is not mentioned that 2% or 5% tolerance limit. Now, just for more accuracy, let us consider 2% tolerance. So, that will give you 4 by zeta omega n. Therefore, by using this formula, for system 1, we will get, let us say TS1, that is 4 divided by zeta value is 0.5, omega n is given 3 radian per second. Then for system 1, this numerical value, it will be 2.67 second. In the similar way, when you calculate for system 2 settling time, again same formula, 4 divided by zeta value is 0.342 multiplied with omega n is equal to 1. This value is 11.69 second. Okay. Therefore, by seeing these two numericals, we can conclude settling time of system 2 is more than that of settling time of system 1. Okay. So, this is the answer. Now, let us look into question number 2. This is came from 1 mark exam. So, one block diagram is given. We need to find out what is the overall transfer function of the system. So, here in a simple terms, you can find the transfer function by using SFG concept, signal flow graph concept. Therefore, first let us look into forward paths. So, forward paths M1 is equal to, now here there is a minus sign. Because of the minus sign, the forward path gain will be minus G of S, and delta 1 is equal to 1 minus, you should take any loop gain that is not part of the first forward path. You don't have such combination, and hence it will be simply 1. Next one, individual loops. Individual loops. So, individual loops L11 is equal to, so this is one loop, hence I can take G of S, and L12 second individual loop, that is another loop in that way. So, that is minus G of S multiplied with minus 1. This will give you G of S. Therefore, delta is equal to 1 minus L11 plus L12. this is equal to 1 minus 2 into g of s. 1 minus 2 into g of s. Therefore, the overall transfer function of the system C of s divided by R of s is equal to m1 delta 1 divided by delta. This will give you minus g of s divided by 1 minus 2 into g of s and hence option A is the correct answer. Now let us go to next question. This question is from time response analysis. Consider the cascaded system as shown in the figure, neglecting the faster component of the transient response. Which one of the following options is a first order pole only approximation such that the steady state values of the unit step responses of the original and the approximated systems are same? So out of these four options, one approximation will be approximately the step response of the given system. Now if you see the pole zero locations of the overall system, the overall given system, you can notice that there is one pole at -1 and another pole is at -20 and there is a 0 at -40. This is the pole 0 diagram. Now in this case a pole that is much deeper into left hand side of the S plane, now neglect this pole. Okay, this is a concept of dominance concept, neglect this pole. Therefore the overall transfer function you can say it is approximately equal to k divided by s plus 1. This is a k divided by s plus 1. But what is k here, where k is equal to DC gain? So that will be limit s tends to 0, s plus 40 divided by s plus 20. So this will give you 40 by 20 is equal to 2. Therefore the required transfer function is equal to 2 divided by s plus 1 and hence option A is satisfying the given answer. Next, question number 4. Now here consider the stable closed loop system shown in the figure. The asymptotic body magnitude plot of g of s has a constant slope of -20 dB per decade at least till 100 radian per second, with the gain crossover frequency being 10 radian per second. The asymptotic phase plot remains constant at -90 degree at least till omega is equal to 10 radian per second. The steady state error of the closed loop system for a unit ramp input is. Okay, now in this problem, if you understand carefully the given statement, what is mentioned that the magnitude plot, let me take dB on y axis, frequency on x axis. The asymptotic magnitude Bode plot g of s has a constant slope of -20 dB per decade at least till 100 radian per second. Okay, so that means initially the slope is -20 dB per decade, at least omega is equal to 100 radian per second. After that we don't know what is the slope, and it is also mentioned that the gain crossover frequency being 10 radian per second. What do you mean by gain crossover frequency? The frequency where magnitude plot is crossing 0 dB line. So that is given 10 radian per second. Okay. Now the question is, what is the steady state error? So by seeing here the initial slope of -20 dB per decade, you can say that the given system is type 1 system. The given system is a type 1 system. So in this transfer function, G of S has the structure of K by S into some factors. So, wherever this initial slope line crosses x-axis or 0 dB line, that will be K value. So, K is equal to, from this problem, we can say that 20 radian per second. Why? Because in the initial slope, I can say here G of j omega is equal to 1. So, that will give you K by omega magnitude is equal to 1, and hence K is equal to omega. So, that omega is given as a 10 radian per second. Now, so this K, you can also consider that KV, static error constant. Okay, why? Because KV is simply nothing but limit S tends to 0, S into G of S. So, that S will cancel out, and finally you will be remaining with the KV is equal to K. Now, under this condition, what is the steady state error of the ramp function, unit ramp function? So, that value will be 1 by KV, as K is equal to 10, 1 by KV value will be 0.1. So, for this question, the correct answer will be 0.1, and as per the official key, any number you enter between 0.09 to 0.11, this range is considered as a correct answer. Okay, let us move to the next question. Consider the closed loop system with G of S is equal to K into S square minus 2S plus 2 divided by S square plus 2S plus 5. The root locus for the closed loop system is to be drawn for 0 less than or equal to K less than or equal to infinity. The angle of departure, you have to take the value between 0 and 360 degree. The angle of departure of the root locus branch from the pole -1 plus j2 in degree. Now, from the given transfer function, the first step what you can understand, or you can calculate, where are the open loop poles. So, open loop pole locations are -1 plus or minus j2, and open loop zeros, they are located at +1 plus or minus j1. Okay. Now, with this, I prepared a slide to show you quickly the pole zero diagram for this given system. So, the pole zero diagram will be something like this. Okay. So, 1 0 is at 1 plus or minus j1. So, plus j1, another is a minus j1, and the poles are located at -1 plus or minus j2. Therefore, if you consider a point epsilon is very closer to root locus diagram, and the root locus diagram is leaving in this direction, then how can you find angle of departure? By simply applying angle criterion. So, how to write down that angle criterion? I can say here, by angle criterion, you can take minus theta 1 plus theta 2 plus theta 3 minus theta 4 is equal to odd multiple of 180 degree because of the negative feedback system. So, the 0 contributes positive angle, pole contributes negative angle. Therefore, if you substitute these angles, minus theta 1, now what is theta 2? 90 degree plus tan inverse. Now, here opposite side is 2 by 1 plus theta 3 is 90 degree plus tan inverse, opposite side is 2 and adjacent side is 3, and minus theta 4 is 90 degree is equal to 180 degree. Therefore, minus theta 1, we can cancel 190 here, and minus theta 1 plus 90 degree plus this value is tan inverse 2 is 63.43 degree plus 33.7 degree is equal to 180. Therefore, from this you can calculate theta 1 is equal to 7.13 degree 7.13 degree. But the correct answer range as per the official key, any number you enter between 4 to 8 can be considered as the correct answer. This is the root locus question. So, nicely given question. Next one, due to space adjustment, I splitted the question like this. Consider the stable closed loop system shown in the figure. The magnitude and phase values of the frequency response of G of S. Now follow carefully. This is the frequency response of G of S. Okay, not complete forward transfer function. Next, given in the table. What is the value of gain Ki for a phase margin of 50 degree? Now, what I can do here, first let us find or let us write down the definition for phase margin. So, what is the phase margin definition? 180 degree plus phase angle of the forward transfer function at gain crossover frequency. Therefore, that will be minus 90 degree plus phase angle of G of J omega GC is equal to 50 degree. Okay, because of denominator S, it will contribute a phase angle of minus 90 degree. Therefore, phase angle of G of J omega GC is equal to minus 40 degree. Okay, minus 40 degree. Now, if you look into the table, corresponds to minus 40 degree, the frequency is 0.5 radian per second. Okay, and corresponding omega, that is called gain crossover frequency, 0.5 radian per second 0.5 radian per second. Now, but what is the definition? But at omega is equal to omega GC, the gain of the forward transfer function is equal to 1, absolute values. Okay, therefore, how can I write down here magnitude of K into G of J omega GC, okay, G of J omega GC divided by omega GC is equal to 1, right? Therefore, K, now this is basically Ki, so Ki into plus 20 log of G of J omega GC minus 20 log omega GC is equal to 0 decibel. Okay, therefore, Ki plus at what is this value? At omega is equal to 0.5 radian per second, the magnitude of G of S is given as minus 7 dB, okay, minus 20 log omega GC value is 0.5 is equal to 0. So, from this, by solving Ki value, it will give you 1.12. By solving this, you will get Ki value is equal to 1.12. Answer is 1.12, but the accepted range, the number anywhere you enter between 1.11 to 1.13 can be considered as the correct answer for this question. Okay, so these are the questions given in from the control systems subject in GATE 2024 electrical paper. So with this, I will conclude this video. I am Shankar, working as a faculty at Om Institute, Hyderabad. I will deal two subjects. One is power electronics, which is for purely electrical students, and control systems. It is for EEE, EC and instrumentation branches. So with this, I will conclude. If you are interested in GATE or AA coaching, you can call the number showing on this slide, or you can visit our website ominstitute.com. Thank you for watching.